Welcome, everybody, and good morning. I'm glad that you're able to join us this morning. We are going to have the final presentation on the Determining the Toxicity of the Materials project. We have Keith Pilgrim from Bar Engineering. He's been the PI on this project, and he's going to be our presenter today. So I have asked you to mute your phones, but despite that, I also want to emphasize that we really want this to be an interactive discussion. So I really encourage you to feel free to pull yourself off mute or to use the box that's a part of GoToMeeting, and feel free to ask questions as you go along the way. So without further ado, I am going to turn it over to Keith Pilgrim, and he's going to tell us about the findings of the Testing the Toxicity of Deicing Materials project. Go ahead, Keith.
Thanks, Colleen. So my goal today with this presentation is to generally introduce everybody to reasons for this study, how the study was conducted, and then run you through some of the results, helping you understand some of the details. You can go back to the report and look at all the results as needed. But the basic principle, what I'm going to try to accomplish today, is enable you to be able to interpret that report based upon what I show you today, and also provide some of the conclusions of the study. And I want to let everybody feel free to ask questions. So this is interactive, so we don't have to lose people while I'm presenting. At the end of each slide, I'll just ask if anybody has any questions. All right. So the study that we conducted was a laboratory-based study to identify the aquatic toxicity of liquid de-icing chemicals. And 3 species were chosen as the guinea pigs of the aquatic toxicity evaluation. The 3 species we chose are presented on the right of the screen, and those species are Ceradaphnia dubia, which is a zooplankton and is a very common species in waterways, and it's a very sensitive species, and it's used for regulatory compliance testing in the United States and many places around the world. So it's a very common testing species that is used based on the food chain, but has many uses as an indicator of aquatic toxicity. Fathead minnows, which is also a commonly used fish test species for compliance purposes and is well known in terms of culturing. And then another test species which is not as commonly used but was also used for this study is the algae called Selenastrum capricornutum, and it is a large algae also used in compliance testing, standard EPA type testing organisms. Any questions? Okay, I'll move on to the next slide then. If you go to the next slide, it is, if I'm able to go on the next slide, here we go. This is a picture of the testing lab, or atypical aquatic toxicity testing lab. It reminds me of a couple things about laboratory aquatic toxicity testing. And that is, it's a controlled environment. It has a water bath, as you can see there. All these cups are placed in a controlled water bath, 25 degrees Celsius. It's a controlled environment. The test species are placed in those cups, and this kind of testing is called static testing. The test species, fathead minnows, and the algae, and the Ceradaphnia, often called water fleas, are all placed in these cups, and that is placed to reside during the course of the test. The other type of testing that is often done is called flow-through testing, where water flows through a given tank. That kind of testing is usually done for fish, and is not so applicable for algae or Ceradaphnia dubia. This testing is usually used for compliance type testing. So it's a well known and well established type procedure. Another thing this reminds me about is feeding. During some of the tests, there's feeding is conducted. So fathead minnows get a certain kind of food during the test. So does Cerdaphiidubia and the algae don't get fed, but they have a nutrient broth that they're provided throughout the duration of the test. So this is a standard, typical laboratory testing setup. And this is actually the lab that we use in the study. Well, on the next slide, slide 3. So here's a study design. The study design is consists of acute and chronic toxicity testing, or evaluation of acute and chronic toxic effects. For most regulatory type, compliance type testing, the acute test is used often for stimulating conditions where you have a larger water body and you have dilution of a runoff or discharge into that water body. And it's a small zone in which species will be exposed to a discharge for a shorter period of time. And acute testing for our study was 48 to 96 hours test. 48-hour test is for the Cerdaphiidubia, 96 is for the fathead minnows. And in acute test, you typically measure survival. So it's a mortality type test and indicates kind of dramatic and large toxic type effects. Whereas chronic testing is done in a longer exposure period, and it simulates, perhaps the tail end of a storm event, which is more applicable to maybe deicing products as they go in the environment, where you may have a short-term runoff effect, which would be acute, whereas the longer-term period would be more chronic, as the chemicals wash off the waterway and maybe are inhibited on the side of the road and finally lead into the waterway. The chronic effects typically measure growth. So fathead minnows are measured for their growth throughout the chronic test, which is a 7-day test. Cerdaphiidubia, the condition for them is reproduction, how many neonates or babies they produce during the course of the test. And for algae, which is a little bit different, even though they call it a chronic test, it's really a 4-day test, and you measure growth. And all of those tests you also can measure, except for the algae, survival, also during the 7-day period. So what you do is you get data from these tests, and you try to summarize them with these toxicity tests using what are called endpoints. And I'll talk about these endpoints throughout the course of the study, but I wanted to find these right up in front here so you can understand what these endpoints are. And these endpoints are indicators of chemical concentrations that are toxic. So oftentimes if you go to slide 4, oftentimes these endpoints are defined as LC50s, IC25s, IC50s, and NOx. These are the endpoints we use, among others, in the study. And the LC50 is typically used for the acute study, the 40-hour to 96-hour tests. And that is the point at which there's 6% reduction in survival in the test. So the concentration of the product in which there's a reduction, 6% in survival. IC25, which is used for the chronic testing, is typically identified as the concentration at which there's a 25% reduction in young production, which is the Cerdaphiidubia, or growth, which is fathead minnows. We also consider the IC50 to the concentration at which there's a 50% reduction in young production or growth. And then there's also a parameter that we consider called the NOx, which is the concentration in which there's no effect. All these different endpoints are compared to the controls. The control from the study was a synthetic laboratory water which no product was added to. And those controls really are used to determine the relative change in young production, growth, or survival among a range of chemical concentrations in the study. Any questions about these endpoints or how they're used? Okay. Moving on to slide 5. For study design, of this is you add concentrations of product into a synthetic laboratory water, which has all the salts and nutrients that fathead minnows, Cerdaphiiduvia, and the algae are needed to grow normally. And you add increasing concentrations of these products into these waters, and then you measure their survival, reproduction, and growth at a range of concentrations. And so from this range of concentrations, yes?
I just want to ask you to pause just for a second. We're getting some audio interference, and I'm guessing there's probably someone out there who does not have their phone on mute. If you could all just check again and get your phones on mute, that would be super helpful. Thanks. And go ahead, Keith. Sorry to interrupt.
No problem. So what you get is it's called a dose-response relationship. Low concentrations, you have a less response. And higher concentrations, you may have a response of reduced dung production, reduced growth, or mortality. And what you do is you get a curve out of this to identify those different endpoints I talked about previously, which help you define the concentration of product in the environment in which there could be some kind of aquatic toxic effect. On slide 6, I gave an example. Oh, okay. So then I'll go on to just talk about quickly about the products we tested, and then I'll talk more about this dose response curve that's developed during the study. Any questions at this point? The 8 products that were chosen prior to the study conducting and during the study, we chose 8 different types of products. The first one was Watershed CI, which is an inhibitor with sodium chloride salt brine. We also chose more of an experimental inhibitor. And feel free to anybody to contribute if you'd like to about these products and how they may apply and how they were chosen. B55 inhibitor with sodium chloride salt brine, Freeze Guard with magnesium chloride, Meltdown Apex with magnesium chloride, Road Guard Plus, which includes calcium chloride, Boost inhibitor with calcium chloride, CF7, potassium acetate-based product, and then Apogee, which is a glycerol-based liquid de-icing product. Any questions? So, moving on to slide 7.
Actually, I do have a question. Sorry about that.
Yes.
I was wondering about the products that you had there, and I apologize you already know this, but I didn't know are they all on the PNS list?
I don't think they all are, and maybe Ron can contribute to that if he's out there.
Yeah, currently all the products are out there except for number 8, the Apogee that has a glycerol base in it. And that was one of those points there was reviewing some of the toxicology that came through with the product. It was submitted, but that's one of the things we're trying to drive out of this study is to define some limits by which to measure future products being submitted to the PNS for QPL acceptance.
Okay, thanks a lot, Ron.
You bet.
Okay. So here's an example of testing that was done with Watershed CI, and it was testing that was done with fathead minnows, and this graph depicts that dose-response relationship that I talked about for a chronic test. The x-axis is product concentration. So we measured out different volumes, converted to grams of product, introduced into a liter of laboratory water. And the laboratory water is water that has a range of cells supporting growth. The control showing no product, and then a whole range of different concentrations. On the y-axis, you have fathead minnow weight, which is a measurement of growth at the end of the test. So these measurements, this is after 7 days of testing. And what you can see is, in general, and I'll get back to the second data point, in general what you have is if you have more product, you don't have much of a response until you hit a certain point there where there's kind of exponential decline in the response of the organism. So this is typical dose-response type of relationship you'll see in a lot of toxicity tests. What we also saw in nearly all the different tests we did is that at very, very low product concentrations there was kind of a stimulatory effect. That typically didn't come into play in the calculations of endpoints which are toxic. So that's a typical dose-response type relationship we saw during the test. If you go to slide 8, also showing the dose response relationship we saw with Cerdafia dubia, and that relationship is with young production at day 7 of the test, which is a chronic endpoint. And that chronic endpoint is young production on the y-axis, and on the x-axis is concentration of product diluted in laboratory water. So you can see the control. There's also a situation where we have low concentrations where it seems like there's somewhat of a stimulatory effect, and then once we get over that hump, you begin to have a reduction in young production. Also, there's this kind of exponential condition where there's a big drop in young production after a certain point. Going to slide 9. This is also pretty typical of Solanastrum capricornatum, which is the growth response from algae. Very little effect as you increase the concentration on the x-axis, and then eventually you get a fairly large effect and reduction in growth in the algae, which is interesting that the product also did affect algal growth, which I did not necessarily expect at the beginning of the test. So those are typical dose responses we saw with the fathead minnows, Cerdafia dubia, and the algae. And for most of the tests we did, the dose response relationship was very consistent, and I conclude that it looks quite good. Sometimes you get very noisy responses, but we had very good, clear responses that allowed us to calculate reasonable endpoints. Overall, the dose-response relationships in the study looked really nice. If you go to slide 10, I just want to point out a couple things that are unusual. If you look at fathead minnows, we also took measurements, in this case for fathead minnows, on day 4 and then on day 7. Day 4 being the acute endpoint and day 7 being chronic. And an interesting thing is that sometimes there's very little difference between the acute effects and the chronic effects. This is survival. We only measured survival for the acute studies, and chronic results are typically measured in weight, but we also measured survival. And that's what I'm showing here in this graph. So sometimes the acute and chronic effects were fairly similar, but it should also be noted that for fathead minnow, the duration is not that much different, really. It's only 4 days versus 7 days. Slide 10 shows that same kind of relationship for Cerdafia dubia. However, typically for Cerdafia dubia, there was a much larger differential between acute and chronic effects. The reasons for that is that Cerdafia dubia is a very sensitive species, and the duration is 2 days versus 7 days for the Cerdafia dubia. Something to watch for as you look at the results of the study, that sometimes the acute endpoints are nearly identical to the chronic endpoints. And that's not a mistake, it's just a function of how the organism responded over those different time periods. Going to slide 12, this is an example of, a graphical example of how we calculate these so-called endpoints. These endpoints are kind of, they seem kind of arbitrary, but I wanted to give a graphical example of how they are calculated. And they're not, they're pretty simply calculated, and it's a linear type calculation. So you can see with fathead minnows in this test, fathead minnows and growth test, that it's simply, I-75 is simply a 25% reduction in growth compared to the controls. And so you can see with this dose-response relationship for fathead minnows and this RoadGuard Plus product, there's very little effect up to 1 gram of product in a liter of laboratory water, and then they begin to decline. And then what you do between that third and fourth data point, it's simply an extrapolation between the two data points to figure out the point at which there's a 25% reduction in fathead minnow weight. And that 25% reduction then is identified with the concentration on the x-axis. So basically I-25 is 2.46 for this particular species in this chemical. If you go to slide 12 or 13, same thing. IC50 is the same type of calculation. You get a 3% reduction in fathead minnow weight, which also represents growth, and that can then be corresponded to a certain product concentration in a liter of laboratory water. So that's how these endpoints are typically calculated. Some of the endpoints have statistical type relationships. The NOEC, which I talked about before, the no observed effect concentration, and the LC50. They also have some smoothing type operations, but in general, the calculations are extrapolated on a linear basis between the chemical and the response of the organism. Any questions up to this point about how we design, the dose response, how we calculate endpoints, and what they're used for? I should point out that a lot of these endpoints, kind of in the regulatory type world, have other meanings. The NOEC, which is the no observed effect concentration, typically the concentration at which is interpreted there should be no effect due to that given concentration of chemical in the environment. Same with the IC25, it's often considered to be a point at which there's no measurable effect from that chemical in the environment. Those are two very important points. The LC50 is also important because it's used for calculation of water quality standards and criteria. So I provided, based upon all that dose response data, LC50s and other endpoints that I calculated, I provided several tables summarizing the results of the study. And here's one of the tables cut out. And I provided endpoints in 3 different ways. And one way I provided was based upon the mass of the product in a volume of diluent, and that volume of diluent somewhat represents the mass of the product diluted in runoff or the receiving water body. So that's kind of the design of the study. And these tables here are examples of grams of product in liter diluent. This is watershed CI inhibitor plus salt, sodium chloride, and here are the different IC25s and endpoints that I've provided. So it's a mass base. And the reason I did that is because a lot of these products have different densities. To make it more simple for the practitioner, if you go to slide 15, I also provided the results on a volumetric basis, basically the volume of the product diluted in a volume of receiving water or a volume of runoff. So the endpoints are different, as you can see. They're not that different, but they are different. It's a simple calculation to figure out if you have a volume of product going into the environment. These endpoints tell you what potential effects you may have on the receiving water body aquatic organisms based upon our toxicity testing results. So, for example, in that first box, it says acute NOEC survival. You can know at that concentration, it's very possible that at that concentration of product, you will not have an acute effect on the aquatic life and receiving water bodies. Assuming that Ceratopsia dubia is a good representative species of that aquatic life mixture you may have in a particular water body. It's a fairly simple calculation for a practitioner to make. Any questions about that? Okay. Going to slide 16. I also provided the results on a salt content basis. So when I got the results, I began to realize that the different inhibitor plus brine mixtures had different salt content. Although they may have the same volume, they have very different salt content. And I want to be able to compare the different inhibitors plus brines such that the different salt concentrations didn't cloud our understanding of the toxicological response. So I gave two products as an example here. One is watershed CI with inhibitor plus salt, sodium chloride, other B55 plus sodium chloride. And what you can see is one is the results are expressed as a concentration of sodium chloride diluted in a liter of diluent. You can see that the endpoints are very different. For example, look at the chronic results. You see the chronic NOAC of the watershed versus the beet product with sodium chloride has a very different toxicological endpoint when expressed as salt. So I should point out that, for example, the chronic NOAC, a high concentration means it's not very toxic, and a low concentration means it takes very little of that product to cause toxicity. So I try to normalize results with three different ways I present these tables so that you can, so the practitioner can use the data as well as allows all of you to interpret the results and be able to separate the inhibitor effects from the salt effects. Any questions about this slide?
Keith, this is Ron Wright.
Yeah.
I think one of the things that we wanted to demonstrate with this slide also was that the concentration of the inhibitors that are being put in a salt brine are vastly different between these two products.
Right.
The watershed CI is 5%, and the beet 55, I believe, was a 30% addition.
Right. Right. So it does help to separate the relative effects of those inhibitors and salts.
On that point, where does it actually show? I guess the other thing I'm looking at too is I see the 288 and 224 there for salt concentration. So from what I believe I see is that the watershed CI actually has a higher concentration of salt than the beet 55. Is that correct?
Correct. That's
okay,
correct.
but then where's the? I guess I missed the concentrations of the inhibitors in there that Ron was talking about.
Oh, we didn't put the inhibitor concentration there. Sorry. But
okay.
Yeah, it's in the report, the concentration of inhibitors. But
not in this slide. Okay.
Not in this slide. But it's somewhat so the B55 and the watershed CL have somewhat similar salt content. However, the B55 is less than the watershed CI. But if you notice, the B55 NOAC is much smaller, meaning it's more toxic for the chronic condition. And when you express that as a salt, it really pops out what the difference is. You can see in that product that 17.6 milligrams of sodium chloride really should not be causing that kind of toxic result. So it's somewhat implied that it's the inhibitor rather than the salt causing toxicity. And in the report, I tried to provide a table of salt-only toxicity, and in the report, I also tried to provide some information about the relative effects of the different products. You can see that in the report. And then, for example, 676 milligrams of salt, sodium chloride, is getting more towards a level that would be toxic. But still, that is a non-toxic level of sodium chloride. It tells you the relative impact of the inhibitor on the toxic results of the study.
Yeah, that's what I was wondering is I should be telling my maintenance guys, don't get lazy and just put beet juice in when you don't really need it. Because you'll hurt the environment more than...
Yeah, I think if we go back one slide, well, I guess slide 15 is not going to help you, but I think if you go back to slide 15, yes, you may want to look at those relative endpoints on a volumetric basis, and someone else who's in the winter in the de-icing community has something to add to this, please do. But it seems like you'd want to look at how many milliliters of a given product would cause toxicity and figure out how much you're actually adding to your road surface to determine whether or not that would cause toxicity. So it seems like there needs to be a kind of a quick calculation. I don't know how effective B55 is relative to watershed CI, so it seems like you need to make that determination to figure out if you want to use one product or the other.
And Keith, this is Ron again jumping in, and some of this is how we had Keith look at this project and try to, you can look at certain, like on this slide or on slide 16, Keith, if you could go back to it. That was looking at the Ceredaphnia dubia, and the way that we tried to approach this was to look at the cause and effect of the minnows, the dubia, the algae, and roll that into a method by which to do a relative toxicity ranking on this. And all things, some things positive, some things negative, but trying to normalize that data. And so what this slide's a little premature. There's the next one that actually shows that V55 is about mid-rank with all things considered into it. But you are correct. There are some best management practices, locations where you're at, on how things could have a cause and effect on the environment around it. Did that help?
Right.
Yeah, that answers mine a little bit. I just didn't want guys to, they'll use beet juice, not beet juice, but salt brine right now, and then as soon as we get this cold front that's coming down, they'll load up their beet juice in it, and then they just may use it all the way through the rest of through February, and not even bother when we're down at 32 to switch, not, drain their tanks and just put salt brine back in.
So this ranking that Ron alluded to, I did a ranking based on all the endpoints, all the results that we gathered, and all 3 species. So there's a lot of data that goes into this ranking. I basically used it to figure out which product is the least toxic and which product is the most toxic. And that considers both acute as well as chronic toxicity. And I did that ranking based upon total product mass, which is also equivalent to total product volume. And then I also did it based upon the salt mass in the product. And that corresponds to the table I just showed. And so I tried to give a volumetric or product mass basis as well as salt content basis of the relative toxicological rank. And so you can see that the salt brine, the watershed CI salt brine, was the least toxic, followed by the 2 calcium chloride products, and then on a volumetric basis or a mass basis, the B55 follows, kind of settles in the middle, followed by the magnesium chloride freeze guard product, glycerol, meltdown apex, and then CF7, the potassium acetate product. So in general, on a product mass basis, it seems like the calcium chloride and the sodium chloride-based brines are the least toxic, whereas the magnesium chloride and the other products with some kind of organic or potassium were more toxic. This follows pretty close to the literature. I think I did this maybe another slide. I may be preventing myself from that conclusion, but it follows pretty well with what I would expect in terms of ranking of salt toxicity. So going from that table to the right there, ranking by salt mass, what that did is it it pushed B55. You know, it's the only difference in the table really was it pushed B55 toward the bottom because it had less salt content. So the endpoints, the toxicological condition of that product was changed because it was essentially more dilute from a salt content basis, which made it seem more toxic then, based upon the ranking there. Any questions about that ranking? There's a lot that went into calculating that. I don't know if there's any questions about the details of the calculations I should go over, or
One thing I was curious about, though, is that for the toxicity, I mean, are we sure that sodium chloride and calcium chloride, magnesium chloride, and looking how they rank and everything like that, separate from the inhibitors, is that the reasons that they rank the way they do? I guess that's what I'm a little confused of. I mean, it looks like the beat 55 inhibitors was causing it to be more toxic than the others, but then again, I'm not too sure that there's no some kind of interference between the inhibitors with the other products as well.
It does. So I don't think the study was designed to necessarily tease out the inhibitor versus salt. It's just something that kind of came out of the results that we noticed. The goal was just to rank them as the product and determine the relative toxicological ranks of the different products we chose to test. However, it does seem like the B55 product is more toxic because of the inhibitor rather than the salt in the product. So it's pretty well known that sodium chloride is less toxic than most other salts except calcium chloride. So sodium chloride and calcium chloride are fairly similar. Magnesium chloride is pretty well known as being more toxic as a salt, and potassium is considered to be far more toxic than most salts. So that's pretty standard out of the literature. And it does appear that it's possible that the B55 is dragging that product down to the lower rankings because of the inhibitor rather than the salt. But we don't really have any evidence to determine that. So you really want to do a side-by-side study with just the inhibitor if you could, and then the inhibitor plus the salt to really tweak that out, which is one of the recommendations for future study.
Right.
Keith,
Sorry, that's a long-winded answer.
Keith, this is Ron again. I noticed also again on the ranking of the salt mass that the Apogee product was absent.
Yeah. Yeah, I can't really do that one because it doesn't have any salt in it, or doesn't intend to have a lot of salt in it. So I had to take that one out.
Okay. I figured that might be a question that come up.
Yeah, that is the reason why. So I talked about this already. I thought I might have a slide on it. Slide 18 just basically reiterates what I talked about in that previous slide. Potassium acetate was most toxic, followed by magnesium chloride, calcium chloride, and then sodium chloride. So I have it. Calcium chloride was more toxic than the sodium chloride product just because of the sodium chloride was the least toxic in both those rankings. From the literature of salt-only type studies, it's potassium acetate greater than magnesium chloride greater than calcium chloride, which is equivalent to sodium chloride. So basically, the calcium chloride and sodium chloride are pretty equivalent. So our study largely followed what was observed from the whole body of literature out there with respect to the salt. Some other observations on page slide 19. Dissolved oxygen. I was concerned from the beginning of the study that dissolved oxygen may be severely depressed because of the organic nature of the inhibitors. But I was somewhat surprised that dissolved oxygen did not drop very low in most of the studies. So what I did is I quickly calculated the dissolved oxygen concentration in the test at the endpoints displayed here. So I figured out the concentration of dissolved oxygen in the particular chemical test at the LC50, at the IC50 for each test species. And I only did that for the IC50 for selenastrum because that's only a chronic test. But basically what this table shows is that during this test, dissolved oxygen did not drop for most of the products to a point which may cause toxicity, but the exception of that may be potentially B55 had a little bit more oxygen loss than the other products. But I don't know if that's really the reason why that one would show up as more toxic. I should point out, and I have a reminder to myself at the bottom of the page, in these tests, they renew the solutions every day. So what that means is they dump out the old solution and they add a brand new one. So dissolved oxygen can only deplete throughout a 24-hour period in the test. So dissolved oxygen kind of gets renewed every day. So you have a high concentration at the beginning of the test and it declines throughout the test to the end of the test. It didn't decline that much, but if we use the same solution for the whole entire 7-day period, the effect of dissolved oxygen may look very different. And there still may be some dissolved oxygen effects in the receiving water body, and that may be a contributor to toxicity. But in this study, because we had daily renewals of the test solution, it did not really come into play. Any questions about this conclusion? Some other observations I made about species sensitivity, acute toxicity, and I'll just couch this conclusion. It seemed that with regards to acute toxicity, the fathead minnow was slightly more sensitive to the products than Ceratopsia dubia. However, the fathead minnow test is, on an acute basis, is a 96-hour test, and for Ceratopsia dubia, it's a 40-hour test. So it's not necessarily a very fair comparison. With respect to chronic toxicity, it's very clear that Ceratopsia dubia was far more sensitive to a 7-day exposure period compared to fathead minnow 7-day exposure period, and selenastrum was somewhere in between those two species. So that's typically what you see in the literature. Ceratopsia is much more sensitive than fathead minnows, and the algae is in the middle. So it follows, to a large degree, what you expect from the literature. I was a little bit surprised that fathead minnow and Ceratopsia dubia were so similar with respect to the acute effects. It may be that inhibitors, and it's a complete guess, may have some kind of added effect to fatheads because they have gills versus Ceratopsia dubia. I'm not sure. Slide 21. General conclusions of the study. I think the study went very well, and so we provided a very high-quality data set for the liquid de-icing products that we tested. So we had very nice dose responses. We were able to calculate reasonable endpoints, which also allowed us to calculate those rankings. I think you can use these data to make some estimates of potential toxicological impact on receiving water bodies, recognizing that the receiving waters may have somewhat different chemistry than the laboratory water we used in the study. The laboratory water consisted of basically dissolved salts, the minimum dissolved salts needed to allow proper functioning of aquatic life. Receiving waters may have different conditions with respect to temperature and chemical composition than the laboratory water and laboratory conditions we provided for in the study. We don't know what the actual impact may be without understanding how these products may be retained along the roadway. And we need to know the dilution effects in the receiving water body. I think other things to think about are the use of the acute and chronic data. where the acute data apply and where the chronic data may apply, and it may depend upon the characteristics of a particular region of the country's storm length or hydrograph. The use of acute data may be more applicable to short storm events, whereas chronic data may be more useful to longer type storm events. And also the use of the acute and chronic data, I think, depends upon the size of the receiving water body and what kind of water body. If you're discharging into a lake, definitely the chronic toxicological data would be used, whereas a large river, it may be more applicable to use acute data. And I say that for large river water body, largely because I think, as we all know, discharges into larger rivers tend to hug banks and have a smaller mixing zone. Like I mentioned before, the study was done at 25 degrees Celsius, which clearly is not what happens in the natural environment during a storm event of snow. And the toxicological effects may be enhanced or reduced at lower temperatures. I'm not sure. For some chemicals, they are more toxic at low temperatures, but it's possible that the lower temperatures may also reduce the apparent toxicity. We don't know exactly how these products will behave in the environment at low temperatures and how they may affect the dissolved oxygen levels. Product retention decay is something also to consider when determining potential effects of these chemicals in the environment. We don't really know what the appropriate exposure period is. So we did studies for 48 hours, 96 hours, and 7 days. And it's possible the exposure periods may be lower than that. So maybe if you have a storm event, the organisms are maybe exposed only for 8, 10, 24 hours rather than a full 7-day period. And how those short-term effects may manifest themselves, we don't know. So there have been a lot of studies on this for summertime when bridge deck runoff goes into water bodies. And you may have only a 6-hour or 10-hour exposure period. We don't know how these chemicals may behave with a very short exposure period. So that's the end of the presentation. Any questions?
Yeah, this is Cliff talking about, the leaching from our roadway into the rivers or into our bodies of water. We may not transport as much during the snow event as we might leach out during the summer when we get rains and wash it onto the rocks, and then maybe it dries and another rain washes more down. So you're saying that the stuff around the edges of the streams and stuff are sounds like they're going to be more toxic, but they're going to also eliminate possible food sources in the algae for the fish?
I guess what I'm just trying to point out is if you have for example, a road deck and all the runoff goes right into a pipe and right into the river, that's the most applicable condition for this study. So you could take these toxicity testing results and estimate the potential effect on the receiving water body using these results. So, for example, if you want to figure out what amounts of deicing product will not cause any toxicity at all, you could use that NOAC value for a particular chemical. Use it for adapting UV, for example, and calculate how much runoff to go off that road deck into that pipe, into that stream, and not cause toxicity. That's pretty much, I would assume that's an unusual situation, and that for most part, you're going to have situations where it's not going to go directly into that river, and it may wash onto soils and plants alongside the road and be inhibited from going directly into the river. So we don't know how that may affect actual toxicity in the receiving water body. Just want to point out that it's not, this data can't be just simply used to figure out exactly what the toxic impact may be, but it can be used to make a very conservative estimate of what the impact may be.
Okay, thanks.
Any thoughts about that, Ron, or anybody else about the use of the data?
Well, I think one thing to add in here is that typically during the winter events is, to come back to what you were talking about here is, that's typically when the moisture is occurring, and we'll see maximum dilution during a runoff event during that. Spring rains or whatever that follow in with that might further dilute some of the impacts into this. But, residual summertime effects on stuff like that, really hard to measure because that's not a point of influx of products into the rivers or streams. Lakes having a chronic accumulation, that might be something to delve into at some point in time, although I'm not exactly certain how we would measure that. But I know with our local environmental group out here, wintertime is typically, the way they look at it is, things are going to happen. We got to use products and chemicals. And some of the impact from that is not as great as what it would be if we were just using sand. So all things considered, I think that's still needs to be looked at from a best management practice. And when you're using this to look at it is you've got to kind of think of all things in consideration and not just saying, oh, I've got this. Because there are lots of additional things to include in with that assessment.
I guess I consider it to be good starting point data in that assessment.
Yeah, and that's kind of what we were trying to do, is do a foundational startup. So, Keith, from this, is there, one of the things that we were always looking from, is there like a minimum set that we can derive out of this from using your normalization of data for when future products come in as an evaluation to look at some kind of an equation to stand by to look at products that would be considered acceptable to the environment, or we have a bigger issue? Because even though potassium acetate showed up as being very toxic, we also know that it biodegrades fairly rapidly in the environment, and some of the toxicity, as we've shown in this study, is immediate effects, but the chronics are not as detrimental as some of the others may be.
Right.
So I guess that's a two-point question.
So you're looking for some kind of equation.
Could we derive from this work a way to look at the impact from the fish, the algae, and the Ceradaphnia, using their numbers, mass of the salts, whatever we need to look to build an algorithm to look as a kind of a cutoff point on material when it comes in? That's where we want to try to get at some point.
I think if you do, say, replicate the toxicity work that I did for whatever future product you look at, I think the best way to look at it is milliliters of product per liter of diluent. So how many milliliters of, I have slide 15 up here, of watershed CL. If you have more than 9.4 milliliters per liter of receiving water, will it start have toxic effects in the receiving water. I think Ceradaphnia dubia is one of the most sensitive out there. It's not, typically the most sensitive species in receiving water, and that is definitely a very conservative metric for assessment. But there's a lot of studies that show that Ceradaphnia dubia is also analogous to aquatic insects, which are really important for streams. So using those results, NOx or IC25 will give you a conservative estimate of what kind of level you don't want to breach. So it's going to be specific to your receiving water body typical flows, right? So it's going to depend upon dilution. But I think, in my opinion, NOx and IC25s are good ways to determine whether or not you're going to have any toxic effect at all in a conservative species of Cerdapnia dubia. And expressing it as milliliter product is a good way to make that simple calculation. If a gallon discharges, applied on a certain roadway for a certain length, washes off into a river, will that have any effect? As long as you know the volume of that river or flow rate of that river and your application rate, you can make that simple calculation.
And that's, I guess, the one step that I'm glad that you helped clear up, because it does depend on the volume of water that it is being discharged into.
Right. I think you had a typical spreadsheet you sent me of how much pollution occurs in the road neck in certain parts of the country. And then the next step is, what are typical flow conditions or low flow conditions in the receiving water body for that particular stretch of road. When I did this study for NCHRP, we kind of found out that the larger the road deck or bridge deck size, I guess, also correspond to the larger the river. So there's kind of a ratio between those two things. So things like that, I think, can be useful as well. So unfortunately, there's going to be a need for some site-specific information.
Thank you. It always comes up as, can we just draw a line in the sand and go? And it's not that simple.
Yeah, unfortunately. It does depend upon your receiving water body.
Are there any additional questions for Keith at this point?
One question, what is the effective temperature on this? Is the temperature you run the tests on in the lab, is that the same as the water temperature we would typically see during snow and ice season? And does temperature have an effect on this?
The temperature we did a study at was a standard EPA testing temperature at 25 degrees Celsius. So it's much warmer than you expect your receiving water body to be at. So I think that if there was any stress due to oxygen, if there is any stress due to oxygen, you would see that at that warm temperature. So colder temperatures in the receiving water body, you'd see less of an oxygen stress. The effect of salt at different temperatures, my guess is, and it's a big guess, is that you'd have greater toxicity at higher temperatures. However, I know there are chemicals out there which there's greater toxicity at low temperatures. So the temperature difference, I'm kind of punting, the temperature difference is not known. It may be that these chemicals might be more toxic at low temperatures or less toxic. I just don't know until we do the tests. To do the tests at lower temperatures can be tricky for cultured species in the lab. You can test Cerdapnia dubia at lower temperatures, but it doesn't do quite as well. Same with fathead minnows. So there's no whole lot, another layer of experimental work that will be required to figure out that question.
I had a question about the water that was used in that. Be it that our waterways and that have a little bit more sediment and that type of thing in it. I know there was any consideration on that as well, is that we'd have a little bit more particulates and clay particles and things like that. It could maybe even grab hold of some of the deicers and keep them away from some of the other organisms. I know with herbicides and that kind of reacts that way. I know there's any thought of that as well, if, in the typical water runoff parkways.
Right. I don't think that any the particulates would affect the salt component of the deicer in terms of its capacity to be toxic. Like you mentioned, the organic inhibitor may be affected because it would, maybe bind up with the particulates to some degree, which seems very possible to me. So it may be that there might be some change in the toxic effect of the inhibitor due to the more silty nature of the stream. Again, these kind of things can be evaluated by taking the inhibitor or the product and doing your testing with actual receiving water body. If there's some curiosity about doing that type of experiment, it's done all the time for compliance testing for municipal and industrial facilities where they actually have to take the receiving water body and use that as part of their dilution series. So it's not uncommonly done, and it can be determined what the impact is, but it's not known this time.
Well, it sounds to me like we're probably wrapped up then. If you do think of any additional questions or you have comments on the final report or the 2-page summary, please send me your thoughts right away. We'd like to get this project wrapped up in the next week or so. And I just want to thank you, Keith, for doing such a good job and giving us a great presentation. We really appreciate it. And thanks to everyone on the committee for your help and support through this project.
Thank you much.